things we're going to talk about today, we're going to try to cover some of the concepts that you should start thinking about as you are designing a program. We are going to be talking primarily about MPI, the standard, not MPI, the implementation running on the machine that you are interested in. Be happy to answer as many questions as we can about the latter, but I want you to think about what you're going to see here as things to consider when you are looking at designing a program for a machine, both this year and in the upcoming years. Ability of the implementations to take advantage of the features at MPI, the ability of the hardware to exploit the features continues to change and improve, so things that may not work well this year might be exactly what you need to get the best performance in upcoming years. And I'm going to start with an example that illustrates some of the things that you have to start thinking about as you're looking at performance at scale. A few of you may have seen this example, and it's in fact a quite old example. The point that we want to illustrate here is that even when you're doing something fairly simple, so we're going to be doing a halo exchange for a mesh, so sending the Go cells to the neighboring nodes. Simple ways of writing it might have unintended consequences. And this example I'm going to show, again, is fairly old. It dates from before there were SMP nodes, before there were multiple cores, multiple processors on a node. In the modern world where you have that, the situation is in many ways much worse, although it's a little different than the example I will show here. But the thinking about it is the same. If we look at an example here, so this is a 3x4 mesh, so think of each of these little boxes as a patch of a mesh that you might use for the discretization of a simple PDE. And I'm going to have to send my Go cells, the values that I'm going to need to easily apply my stencil locally. Right? So if my stencil sticks out, if I have a simple, for example, I have a 5-point stencil, then this corner piece here is going to need this data value and this data value. What we normally do is make copies of those by sending that appropriate data to each of my neighbors, and then I can easily run the loop. I hope most of you are familiar with this. And the arrows here show the communication pattern. So each of these processes is sending its edge row of data that it owns to its neighbor to be used as the source of Go cells. I was talking to a group that was having a problem getting this to scale many, many years ago. And they said, well, first we did this, sent the data, and they received the data. And the reason they had done this, I think Rusty last night mentioned that one of the early machines that provided message passing, even pre-MPI, provided very generous buffering. So what that meant was on that machine, when you did the equivalent of a send, it would make a copy of that data somewhere. And so you could write. So this is nice, very easy to write this code. What's wrong with this code? Well, it can deadlock, right? The worst possible case. There's no guarantee that it will deadlock because MPI implementation is allowed to make those copies. So what does that mean? It means that code would work fine until you had to do a demonstration in front of your boss or a live demo in front of an audience, at which point that's when it would fail. They understood that. Well, there are some variations. For example, I can do, if it has a down neighbor, I'll send. If it has an up neighbor, I will do a receive. This no longer deadlocks, but it has another problem. It sequentializes. So the code is correct, the code runs, the code is not parallel, at least in the communication. So this is another aspect of the code works, but in some sense fails, because one of the things that you want to be achieving with parallelism is more performance. This is why one thing that I'd like to encourage as you develop these programs is have some sense for how fast you think it should be. All too often, when we're talking with even the application developers for big machines, their notion of that the code is performing well enough is that it printed a nice number when they asked how long it took, not that they had anything to compare that number against. So I'm not saying you should compare that number against the peak performance, the peak flop performance, because that's not relevant. But you should have some notion of how long, for example, the communication step should take. And if you're not seeing that, then you may have done something wrong. So in this case, you would see it, because what would happen is something like this. The code that doesn't have to send any data does its receive. That helps it match up with the code that's sending to it, which allows this one to complete and then issue its receive, which then allows its neighbor to start its send and then complete that send and issue its receive and so forth. And so it's quite possible to write MPI communication code that works, and this will work all the time. It will, you can prove that it won't deadlock, but it will always be slow if there's no buffering in the send. So for example, if you were on an implementation that buffering the send, it would be parallel, but there would still be another problem. What problem is that? Well, it would have to work because it was buffering, which would mean that it was making a copy of the data. What did that copy of data accomplish? Well, it uses memory, but other than that, it really accomplishes nothing. It's just a waste, right? It's data motion for the purpose of data motion. It doesn't advance your solution any. The group that was looking at this said, we read about MPI. We read about the non-blocking operations. So we'll do this. We issue non-blocking receives for the various edges, and I've made this fairly straightforward, so I'm ignoring the fact that some of the edges might not be contiguous and so forth. They went ahead and arranged for contiguous moves. So you do all the I receives, and then you do sends. Why do the sends? Well, these I receives as non-blocking operations means that you can't access the data buffer into which the data is going to be received until that completes. You've got to have these extra requests and a wait, and the idea was just, we'll try to make this, we'll make the minimum change to this code that will make it work. And what they found was it was much better. They got parallel communication, but they had figured out how fast it should be, and it wasn't that fast. They were losing performance here, and they didn't know why. And it's in fact quite subtle. And what I'm going to show you is why on the system they were running, there was a loss of performance. On other sorts of systems, you might get different behavior. And so the thing to read from this example is just that you have to think more completely about what happens with the data. And we'll come back to a similar statement, or a similar situation when we look at process topologies and the mappings of work to physical cores in the afternoon. On the system they were running, these things were approximately true. So the sends could interleave. So if you did a send, it can compete with delivery to another process with other sends. The sends do block, so the amount of data that was being moved was enough so that instead of making a copy, the send would wait. I'm going to do a model that just looks at how the sends control the timing. So just look at how the send data moves. And the receives don't interfere with the sends. And if you do that, then this exchange can be done in 4 steps. So if we go back here, I'm going to assume that a 5-point like stencil, so I've got neighbors up, down, left, and right. And so so this is, the number of neighbors is at most 4, so I get that. So what in fact happens? Well, let's assume everybody starts at the same time, and for the advanced people, I just gave you a reason why MPI barrier is sometimes good and not bad. So if you want to think about that. So what happens in the first step? So I'm assuming that the first thing is to send down. So a lot of these processes send down, and I've used these dark or straight line arrows to indicate that the whole edge moves in that step. But what happens, these processes down here, they don't have a bottom neighbor. So they go ahead and go to the neighbor they do have, the first neighbor that they have. In the case of these 2 processes, they both have a right neighbor. This process has no bottom neighbor or right neighbor, but it has a top neighbor. So now what happens is this process is sending here, and this process is sending here. Well, my assumption is that the rate at which data can go into that node is effectively the same as the rate of one of these arrows. So if these sends are interleaving, that means that some of the data from this process gets into this process, and some of the data from this process gets into this process, because there's a choke point as this data arrives. So another way to think of it is, say that each of these sends consists of breaking the message up into 1,000 fragments. And it sends those 1,000 fragments. And this process can eat a certain number of fragments per second from any source. Say it's 1,000 fragments a second. So now this process is receiving 1,000 fragments. It takes 1 second. This process is receiving 2,000 fragments, but it can only absorb 1,000 fragments a second. And so with the sends interleave, basically it will take 500 fragments from its top neighbor and 500 fragments from its left neighbor, which means it will be halfway done in both of those cases. Similar thing happens here. Because this process has no right neighbor, it starts sending to the top. And again, this process is absorbing 1,000 fragments. So its interface is completely busy. But it's getting 500 of them from this source and 500 from that source, which means this send is only halfway done, as is this send and this send. Okay? So as you are thinking about what happens with MPI, the point-to-point messaging often makes us think about the communication by thinking point to point. And what we forget is that that point-to-point communication makes use of a lot of resources that are shared with other processes. So in this case, what's being shared is the ability for data to enter a node and be placed in memory. So in the second step, so these processes, I'll go back. So this process completed sending down, so the next thing it does is send right. So for this process is able to do this, it will do that. These processes, none of these processes have right neighbors. This one doesn't have a top neighbor, so it starts sending to this one. So again, we've got 2 incoming, so it'll get 500 fragments from here and 500 from there. These are just the same as this step because they got halfway through in step 1. They get the remaining halfway through in step 2. Same things over here. Well, that's kind of okay for these guys, but this guy is now behind. In his second step, he should be sending right. Okay, so in step 3, we continue this. Now, this poor guy has data coming in from 3 directions. So he's only going to get about a third of the way through this one. Similarly, this process that should have been sending right in step 2 is finally able to in step 3. So you can see we're already a little behind. And we're behind, again, because the way the communication was set up meant that those sends had to complete before you could go on and try a different send. So if I go back here, remember, in this model of the computer, I mapped these processes onto a network. I'm assuming a nearest neighbor network. There are links between, between the top of this and the bottom of this and so forth. In step 2, I'm not using that part of the network. And so that's a lot of your resource that you aren't using. So, and one of the ways to distinguish a supercomputer, and I heard some of that coming up yesterday, talking about cloud systems and is a supercomputer a cloud system or whatnot. One of the things that distinguishes a supercomputer is a high-performance interconnect. And whether or not you can have that on a cloud system and make the business case for it is not what I want to talk about now. But the issue is the big expense usually goes into the interconnect. In this case, we're not using very much of the interconnect. We're not using any of these links. So we get to step 4, and these guys are still trying to make some progress. At this point in step 4, we should be doing the last shifts to the left. So turns out we get another step here. This guy has to finish. And finally, these 2 processes are able to send their last data to the left. And it took 6 steps instead of 4. So it took 50% longer in this model than you would have expected, because the requirement in the code that the sends complete meant that when your target process was busy receiving data from somebody else, you couldn't make any other progress. And if you looked at, it tells you how old this was on an original IBM SP, if you looked at a plot of it, what you found is these blue things are the sends. In this example, every process is sending the same amount of data, and it's essentially the same type, so it's all contiguous data. So each of these bars should be the same length, and what you see is that, in fact, there's a histogram here. There's a peak here. There's another, you can argue there's another little peak here and maybe a little one here. So this corresponds to the ones that take the time that's expected. This corresponds to the ones that take twice the time expected. And this is the, I think up here is the, remember there's one that I mentioned where at some point you've got 3 processes sending to it. So it's even more slow. And again, you can see that here. Here's sort of what you'd expect to see. Then you see ones like this. And if you map these ranks onto that picture, you will see that the long ones are where you expect. Okay, so what's the fix? Well, the fix is to recognize what the problem is. The problem is that by using a blocking send, you've established an order of completion that's unnecessary. Right? So you want to exchange the halo. Often do not care in what order you exchange the halo. You don't care who completes first, you just want it done. The code that was written, however, insists that that halo exchange complete in 4 steps, each send of which has to complete before you can start the next one. And so that adds an extra constraint, and it makes it impossible to make good use of the network. And I should mention, you can say, oh, this is all this point-to-point stuff. In shared memory, you don't have to worry about this. In some ways, shared memory is worse. What if I had written memcopy there instead of send? Well, the semantics of memcopy is blocking, right? And memcopy doesn't return until it is copied to memory. So if I had written this as shared memory code, the same problem would happen because I would be rushing data into a target node faster than the target node could accept it. My memcopies are blocking, which means that they just have to wait until they get enough memory cycles to move the data. Sometimes it's not as obvious because maybe there's enough spare memory bandwidth, but again, the issue is the same. By specifying the order in which I want things to complete, which I do implicitly anytime I use a blocking operation, I've added constraints that may make it difficult for the system to achieve good performance. The fix is pretty easy. You do iReceives and iSends and wait on all of them. Now this can also be really important on systems that have parallelism in the communication channels, like BlueJean. So one of the ways that BlueJeans have gotten their performance is by having parallelism even in the network interface. So rather than having one honking fast engine moving out of the node, it has less capable engines on each of the links. So what does that mean? That means that for good performance, you need to drive all of the links at the same time, which means that you have to have enough concurrency in the communication available for you to drive those links. So for example, if I write a Halo Exchange benchmark that only provides enough concurrency to drive one link at a time, a machine that has a single really fast network interface will look better than a system that has multiple slower interfaces. I will say those systems can cheat a little by dividing their packets up against the different links, but they also then have to travel a little farther and doesn't match what you're really doing, which is I have a bunch of data, I need to move it to a bunch of processes. Let me let the system do that efficiently. When you call any one of these routines, something will happen. Typically what will happen with an iSend is that when it sees the iSend, it will, and the data size is large enough that it doesn't want to just send it ahead, is it will send a request to send message. What you would like to have happen is that when that request to send message arrives at its destination, what it's looking for there is there a matching receive for this? So as that message comes in, it'll say, okay, what are you asking to do? Okay, I found the matching receive, and I can send back information about how to answer that receive. That might even be, for example, here's the global address into which to write directly. So do a DMA transfer over here. So normally what you want to do is post up the iReceives first so that when one of those packets arrives, you'll be able to respond immediately. There are some other things to do. So for example, for various reasons of implementation to keep things simple, as you add iReceives, when you do any kind of receive, it will look and say, has somebody already sent me a message about this? So for example, say one process was late and some of the ISENDs started to arrive, the request to sends started to arrive before the receive. So it would look and try to match up to those sends. It has to provide the appearance of ordering. So what typically happens is that there's a queue of receives and a queue of unexpected sends. And what you would like then is to minimize that queue search time. Right? So in a case here where I've got 4 neighbors, who cares? But in more complex codes, you might have 20, 30 neighbors. That can make a difference. So the order in which you post the receives should at least try to match the order in which you might expect the sends to arrive in. So that when you look at the queue, what you find, when you look at the top of the queue, what you find is the thing that you're likely to be looking for, just to reduce the queue search time. The other thing is, in this case, notice that I passed the rank of the neighbor. A lot of people say, oh, I just don't want to worry about this, and put any source there. Okay, bad idea. There are ways that you can optimize working out this queue match that are more efficient if you don't use any source. In fact, there's remains active discussion in the MPI forum about allowing the user to provide the promise that they will never use any source. And if the user keeps that promise, there are some really nice things that can be done to improve the performance at the sort of bleeding edges, particularly when you have more than a handful of messages in this queue. The other thing is, by avoiding any source, you eliminate one possible source of problems. When we look at, you look at this loop, most of us tend to look at this loop and forget that, for example, this loop is in a bigger loop. And because you're iterating over this thing. And if you're not careful, and you make just small changes to this code, there can be opportunities for one of the sends in the outer loop to connect to a receive in a previous loop. And those bugs are ones that you just tend not to see because you don't look at the code that way. Right? The way we handle complexity is we break it down into smaller problems, so we look at the body of the single loop. We almost never think about the cross-loop problems. That's where you can get some challenges. By being careful about the order in which you issue these, a choice of tags, these neighbors, you provide much more information both to the programmer and to the system about the order in which you expect to do things. One of the nice things about message passing, to emphasize one of the points that Rusty made yesterday, is that one property that I think a programming system should have for parallel programs is that if you have a deterministic algorithm in the weak sense, so if I give it certain input, I will get the same output every time, then my programming model should allow me to write that algorithm in a way that obviously preserves that determinism. It's hard to do that with straightforward shared memory. It is easy to do that with message passing as long as you avoid wildcards. And guaranteeing that determinism is a great way to avoid having to find bugs. One of the exercises that you can look at, we're going to provide the code. In fact, that's the code that we mentioned last night. You can take that code and try different orderings of these and see how they behave. You can do something similar with more neighbors, see what the effect is. Okay, when you do this, again, you allow communication everywhere, and what you get is much more predictable performance. These two are longer because they are these two processes, the only ones that have 4 neighbors. So The thing to remember here is that when we talk about message passing or talk about parallel computing, people tend to focus on moving data, because that's why we're doing this sort of stuff. We're moving this data. What they tend to forget about is that you also have to synchronize. And by synchronize, I mean both the source of the data and the target of the data have to know when they can use the data. And that is what is hardest. It's hardest in shared memory models. It's even harder, in the distributed memory models, message passing models, it's even harder in shared memory. And so as you're thinking about parallel programs and getting performance, don't just focus on the data transfer, particularly don't just focus on the data transfer from your point of the program to where it lies. Think about the whole path that the data transfer runs and what sort of synchronization you have on it, what sort of constraints you're making for the order of completion of the operations. When we look at applications, we often see much more synchronization than is required. So that means using blocking sends in too many places. That means using non-blocking sends, but doing one edge at a time. So I do I receive, I send, wait. Just doesn't really accomplish a lot. There are, unfortunately, a lot of benchmarks do it the wrong way. So for example, if you want to see how to write code for Halo Exchange, under no circumstances whatsoever even acquire, much less look at, the NAS parallel benchmarks. Okay? They're just terrible. They were originally written for the Intel NX system, which had sends that did lots of copying. And there was no wait-all equivalent. So there was no way in the original system to write them like you can in MPI, and they were never modernized. I do have an undergraduate student looking at doing a nice modernization of them. So that's one of the lessons. It's something that you'll be able to explore a bit today. I will say this approach is not guaranteed to speed up every code on every system. In particular, again, for a machine like a Blue Gene, one of the things that's most important is to be able to drive the right number of links concurrently. That does mean making sure that you do multiple iSends so that you give enough information for each of the links to be busy. But one has to be careful there. One way to slow things down is to have too much of that. So, for example, if you think about doing an all-to-all implementation on a big machine, you could say, okay, this is what Bill has just told me to do. I'm going to do, I have 16K processes, so sort of small. I will post 16K I receives, followed by 16K I sends. Right? Is that a good idea? No. Remember, among other things, for point-to-point communication, I have to do this matching. I have to match a sender with a receiver. There are certainly ways that I can implement that match that was efficient, but for typical uses, where I might only have a handful of sends and a handful of receives, a linear list is really, really good. In fact, it's essentially the fastest way to do it. There's a point where, of course, linear list becomes really bad, but there are all sorts of ordering criteria in message massing that have to be preserved, so you can't even go to a simple, more complex data structure. You have to go to a more complex data structure. And most implementations haven't done that. So you may need a little more synchronization. What's the threshold? Will depend on the implementation, the kind of hardware you have. So for example, for a machine with a 5-dimensional torus, you need to have enough posted iSends and iReceives to keep all those links busy. For a system that has one big fat pipe but has adaptive routing, again, you may need to have a couple of sends busy to allow there to be enough work, enough communication work to keep the whole network busy while things are choked. Okay. In many cases, if you properly modularize things, you can make it relatively easy to swap in and out different ways of doing that. And the example code it shows a little bit of that for a fairly simple example. So it has a set of exchange routines. There's a thing to initialize the actual exchange and a thing to complete. And things are organized so the appropriate parameters can be passed back and forth and so forth. And that means I can just pick the one that works best on each system, okay? But I would have to maintain them all, right? So the answer to the other question is, what could I do that would probably give me good performance most of the time? That would be this version, something like that, with some variations of this. There are some cases where you might want to post the ISENs first, but typically if you do the receives first, iReceives first, then the ISENs, you do them in an order where if they all start at the same time, they're likely to match up in the queues, which is not quite this order. And you don't do too many of them. So you can set a threshold. If I have more than 20 neighbors, I need to think harder. That should give you pretty reasonable performance. The other thing, though, is you should know what you expect. So why not have the code tell you when your rule of thumb isn't good enough anymore? That's another thing that I would encourage. So particularly when you do rule of thumb, you've implicitly established a contract with yourself saying, this rule of thumb I've decided is good enough to provide the performance. As long as you're within your performance expectation, you spend time elsewhere. But since you've made that assumption, be prepared to act on it. And that means be prepared to be notified about it. And I would say that applies to everything. So if you've got a compute-intensive loop and you think you've gotten it the right way, because it's the same problem. I mean, how do I write a compute-intensive loop that runs well on everything? It's not going to run optimal. For example, for the BGQ, you have to have 32-byte aligned data to make use of the 4 wide vector units. Right? So, how much of this do I want to expose? In some cases, I might say, well, as long as I'm getting good enough performance, I don't care. But if I'm really getting like 1/4 of the performance I expect, then maybe I need to do something else. So again, I think be quantitative about it, and be quantitative. That also means understand what you expect to be able to get out of it. So if what I'm doing is I'm really just doing a gather from a bunch of people to one place, the implementation is likely to be better, particularly if the data is short. The obvious way of writing a gather is everybody does one send to the target who does p-1 receives. Right? Well, you don't have to do that. You can do essentially a reduction, which is a concatenate. So, for example, every odd process sends a couple words to the even process below them. Then those even processes throw a bit off and do that. And you do this log p times, and you get all of the data in log p steps. Most of the processes have done more work than they did with the trivial implementation. But the total amount of time is essentially log p communication steps that will be dominated by the latency costs as opposed to p steps dominated by that latency cost. And a good implementation will do that. So that's an example of a place where by using the collective model, you allow someone else to deal with that implementation. Because it actually gets a little more complicated at large scale. So a really good implementation, as you get down to, say, 1 million processes, you may want to do something a little different. As usual, you don't want to know about that. As you get to larger and larger messages, then the benefits can go away unless the implementation does a lot of really special things for all gather, which they may not have invested in. And in that case, some people have seen that they can do a better job by specializing the all gather for their application. And so again, there's no real answer. The right one to do is figure out what performance you expect to get, see if you can get it with the simplest code, and then be prepared to do a little more work if you have to. When we look at the costs of any of these operations, there's a latency, there's an overhead, and there's then the sort of data transfer time. So there's a certain amount of just cranking through the code. That's the overhead. There's the latency in terms of how much time it takes for the first byte to make it all the way through the network. But there is that overhead. And you can make that overhead pretty small for message passings, but it's still hundreds of instructions and hundreds of cycles. So even a really, really, really tight system, that's going to be 200, 300, 400 nanoseconds. And so, and those add up. Right? So if you can bundle your data together, you can improve that. But what can also happen is say I had a number of short messages, say 3 of them that were 100 words. And if I could send those, well, in a typical system, it would just send those because they're small. So that's single network for them. If I bound them all together, and now they were 300 words, and now let's say that's they're 8-byte words. Now maybe they're past some threshold. Now what happens is instead, I send a single short message, which is, pretty please, can I send this message? Then I have to wait for a message to come back saying, yes, you may, and then I have to send the data. Right? So now I haven't saved anything by doing the aggregation. Right? So this is definitely an advanced sort of topic, but it is the reason why it's hard to give a specific answer to this. One of the things that can often improve the performance of some codes is if you can force the implementation to provide enough buffering so that your messages just go out, and then you write your code, again like this, so that most of the time the receive will be there, but the times when it's not, the system can just buffer it. Right? And that often gives you the best performance, and this is usually called the eager threshold. Right? There's some work going on looking at ways to make the system more adaptive to that so that you don't have to do it by hand, but that, again, can make a big difference. There are a number of different implementations that can be done for all-to-all, and again, if the messages are large, there is a point where it's going to be effectively like this, but that's a good example of the place where I'm on, say I'm on Mira. I don't want to post 500,000 I receives and then 500,000 I sends. So it's typically done there is you break it down into phases, and you post some number of I receives and some number of I sends. It's not trivial because you have to pick a subset. You have to pick a matching subset, right? So the I receives I post have to match the I sends that other processes are posting, and vice versa. In addition, if I'm not careful, I can get hotspots. So I can get mappings where I'm doing all this. I'm doing the all-to-all, and too much data is going through some link or into some node, and get poor performance. For small data, one again can do some of these algorithms that are log P that move more data but take less startup time. And again, it depends on whether the implementation is willing to do what it's willing to do and where that threshold is. So a good all-to-all implementation will deal with all of these issues, including, for example, choosing that subset intelligently. The default implementation in MPI-CH is fairly simple-minded. It does not, for example, it doesn't know anything about the network topology, so it has no basis by which to pick a good distribution. But a vendor can provide a much better implementation, and quite a few vendors have because of the importance for some computations of all-to-all. So again, what do you expect? And try the MPI routine. If you're lucky, it will be fast enough. If it's not, then I've given you some ideas on how to roll your own. I'm going to go through some of the data types. Then what I'm going to do is briefly go through the sort of sample code that we put together for you, and the first set of exercises, which you can then go and do up to the break. Data types is another thing that's really cool in MPI. It's very important, particularly for I/O, because it provides a very general way to describe layouts of data that are not necessarily contiguous. I'll say up front that on many systems, the implementations of data types have been disappointing. So I'm not standing up here saying you need to learn about data types because it's going to be faster, although there are counterexamples. We've had some success, for example, on our Cray in a full application. So benchmarks don't always show the benefits as much. And one has to be very careful about the way you do the data types because there are many ways to specify the same pattern. Typically, only one of those works really well. This is another area where work is going on by a number of groups, including ours, to provide better performance. If you look at the IBM Red Book for the BGQ, it says you should just not use data types or non-contiguous data. But the reason they're saying that is that anything that you do that is not contiguous is bad on the machine. So they're basically telling you, don't even use data structures that are non-contiguous. Well, that might not be an option. Right? So if the data types were done right, you would, in fact, eliminate one of the moves that they're so worried about, because you could gather the data directly from user area into the memory locations where it gets shipped out. What happens now is that you have to gather it together yourself, and then it gets block copied. Right? So this is why the data types, in principle, can provide better performance, and on the Cray, that's why we were able to get better performance. So again, the data types give you a nice way to describe this. They really are vital for I/O. So when you learn a little more about using I/O, the data types become really important, and that's a place where even now they provide significant performance benefits over other approaches. And there are lots of ways to construct these data types. Because it's based on a library, it's a little awkward. We'll confess that up front. Over time, various people have built tools that will take, for example, a declaration of a C structure and generate the MPI calls to create the data type corresponding to that. So for example, because these things can be set up recursively, I can build a data type out of a number of different types. So what do we got here? Well, this type is an index type, and basically is an array of offsets. So I can think of this as an offset. Say there was a 13, a 15, an 18, and a 21, and an array of block lengths. So I could say this was of length 1, length 2, 1, 1. Or possibly this was a 13, a 15, a 16, an 18, and 20, all with block lengths 1. And so that gives me a fairly general layout. There's a contig, which is just, this is a contig of 2, contig of 2, contig of 2. I can create a vector, which is a strided, or take a type and repeat it with a skip. And so this is, say this block of contig, skip 2 three times. And then a struct that contains a vector and an indexed. There are times when you might want to put together a somewhat more complex data type. And in fact, there's an example in the sample code. So to start with, the basic types are the language types. So for a cint, if you want to describe a cint, there is an MPI int. For doubles, there's MPI double. In Fortran, there's MPI integer, MPI double precision, and so forth. That gives you all sorts of advantages. Would allow you to work with systems with different data representations. When MPI started, there were lots of systems with different data representations. There still are, mostly having to do with byte order or byte length. There's fewer places where people build an MPI program that spans systems with multiple data representations. But it also means that you don't have to worry about how many bytes are in an int. How many bytes are in an int? How many of you know the right answer to that question? Yeah, the only thing that C says is that the length of an int is no shorter than the length of a short and no longer than the length of a long. And some of the other integer types. It basically only has to do with how long it is relative to the other types. Fortran, same thing. The length of an integer is not specified, but there are requirements on how long an integer is relative to, for example, a double or a real. So an integer is in Fortran is exactly the length of a real. It's not the length of a double precision, and so forth. If you're writing portable code, if you can deal with MPI ints instead of ints and so forth, you don't have to worry about how many bytes does the system have. So if you go from a system that has 32-bit ints to 64-bit ints, your code should just work. And that's a very nice thing to use the intrinsic data types. And so there is, for example, an MPI byte. This is almost always a mistake. If you see MPI byte being used as a data type, it means that the person writing the code probably didn't really understand what they were doing. There is MPI byte. That means that there are, in fact, a couple of places where it makes sense. Usually, you should be using the intrinsic types. And when MPI was originally defined, it had all the types. Over time, C has added a whole bunch of types. MPI 2.2 tried to catch up, and it has many of the core C types now. So what are the constructors? The easiest one is MPI type contiguous, so that just takes a count of a data type, so data type old type, and gives you a new data type. And so, for example, if these were ints, then if I said 7 MPI int, then I would get a new type that represented a block of 7 ints. I can, that type doesn't have to be a basic type. So, for example, say I had a struct type that described this, then a contig of 3 of those would do this, and then do it again, and then do it again. So why do we, you can use this here, but effectively in a MPI communication operation, you have a count and a data type. That's effectively creating a contiguous data type of n copies of that data type. So that means that you never really need to generate a contiguous type for that. There's no reason to generate a contiguous type and then send one of those. You can send n of the underlying type. But in other places, it can be useful to put this together. Vector is there's a number of blocks that have a certain number of old types in them, and there is a stride between each copy of them. So this is a block length of 2, a stride of 3, and so this is my vector, and it ends right there, which is an important. So these are really good for regular arrays, so Cartesian meshes, matrices, things like that. This allows you to specify the pattern very simply. And so in the example where we have seen good performance, it was with this sort of type, with a vector type. Fairly easy to optimize. There are other programming systems like ARMCI that also have optimizations for example, for strided types, because it is possible to get good performance out of those. The base type does not have to be a primitive type. It can be, for example, here's a struct. So I could have a vector of structs. I can also do a vector, but sometimes when I'm doing the vector, if I look at this, the stride is in units of the size of this old type. And that's often what I want, particularly when I'm doing just a vector of doubles, because I just want it to be a stride. I want it to be 2 doubles every 37 doubles. But sometimes I need it to be a stride that is not an even multiple of the length of that base type. And so that's what there are a bunch of type create functions that have an H in front of them. That allows you to set the stride not in terms of multiples of the base type, but in terms of bytes. That would allow me to do, for example, put together groups of structs and so forth. The next sort of obvious type is indexed. Already talked a little bit about this, where this is what you would use for a scatter or gather. Indexed, and there's also a type create H indexed. So you've got some number of elements, and then an array that tells you how long each one is, an array that tells you what their displacement from the beginning is, and what the base type is, what the old type. So for example, if I was gathering some ints out of memory with an index array, this would be, the old type would be an int. This array of block lengths would probably be, say, 1, which is why there is an index block, where I can say if I'm scattering and gathering elements that are all the same length, rather than pass an entire array of the same values, I will just pass that one length. This was an addition. And just as for vector, where sometimes you want those displacements not to be multiples of the base type, but in bytes, there's an H version. And that's the only difference between type create indexed and H indexed is what is the displacement relative to. The displacement is going to be here in this array. And that's just that's the location of the first one of these. So this array of displacements would have a 0, and then it would have, let's say these were each bytes. So this would be 1, 2, 3, 4. This would be a 5. Well, so when I'm constructing these data types, I'm usually constructing them as relative to some address. I can construct them so that they are absolute. Typically what I want to do is I want to construct this data type, and then I want to use it, say, in a send or receive, where I pass in the origin address of a buffer. And that way I could apply the data type to any memory that starts at a place that makes sense for the data type. There are times when I want to construct something that refers to a specific part of memory, in which case the typical thing to do for these displacements is make them relative to the beginning of a buffer. So the first element of the struct is at 0, and then the other elements are wherever they're at. But I could instead say I wanted to send a particular struct, and then I could use MPI get address to get its address, and use that in building the displacements. But then when I use that in communication, the buffer address that I have to provide is MPI bottom, which is a special address that says effectively the data type contains absolute addresses, not relative addresses. That's rarely what you want to do, but again, occasionally that's what you need. Okay, then there are a couple of constructors that I will call convenience constructors. This is because they don't provide any new capability in terms of your ability to specify a layout. However, they may be a little simpler to use. Type create subarray effectively is a kind of a vector constructor that allows you to specify a subarray out of an n-dimensional mesh by specifying that way. If you want to play around with data types, a good exercise is to figure out how to implement this functionality using the other MPI routines. So using vector, H vector, and so forth. There's also D-array, which is a distributed array, matches data distribution. It was often used, was defined for HPF, and again can be used as a convenience function for building data types for things like regular Cartesian arrays. Okay, so again, they don't provide any new capability. All of these here provide ways to define a data type in a compact way. So in principle, struct can be used to specify any possible layout, but not necessarily compactly. The alignment that you define should be correct for the data types that you're using for your system. So, for example, it would be a bad idea to put a double beginning on a prime number offset. Let's see. I'd have to go back and look to see whether the standard lets you do that, but even if it let you do that, your performance would probably really suck. And so the rule here should be to stick to the language alignment rules. One transition to think about. So right now, most of you have grown up when there was one address space. It started at 0 and it ended at 4 gig or 16 gig or 64 gig. And addresses were nice ints, and you could add and subtract them from anywhere, right? Almost all of you grew up like that, because almost none of you are as old as I am. Right? Well, this was not always the case, and C does not have that model as a requirement. There's no part of the C standard that says that you can take the address of two different objects and subtract them and get a number that means anything. I can take the address of different parts of the same object, for example, an array of structs, and subtract them. That has meaning, but I can't take a variable here and a variable there, do ampersand, cast as longs, and subtract them, and get anything that is guaranteed to mean something. Now, right now, people do this all the time because it always means the same thing, which is the distance in the address space. But as I said, that was not always true in the past. And as we go forward, particularly to extreme scale systems, it's not clear that that's going to be true in the future, that various compromises in terms of address spaces, particularly for systems that, for example, might have integrated different types of cores, might not continue to provide this model of one homogeneous flat address space. And again, C is already ready for that because when C was invented, that didn't exist either. So it's important if you're writing code, even going forward, to make as few assumptions about the address space as possible. So MPI provides a routine, MPI get address, which gets you something that the communication system can use for the purposes that it needs. Right? So if you need a displacement for those arrays of displacement in the data types, the right thing to do is use MPI get address for them. If you were inside of an object, and you'll see this in the sample code, using ampersand to compute a relative displacement is correct, even in C, but not, again, not between different objects, not between variables, different instances of a variable. And so it's important to be careful about that. Now, another thing that some people overlook is that constructing a data type is a two-step process. Quickly talked about sort of constructing a data type, but then you have to prepare it for use in communication. And that's done with MPI type commit. And you might say, well, why doesn't everything come committed? Well, I might build my data type recursively, and I'm uninterested in using the intermediate data types for communication, just the final data type. And the process of commit might be non-trivial. It might do all sorts of optimizations. It might, one project that we're working on, it might generate new binary code to implement the data type. Right? So you don't want to do that except when you have to. And so that's why data types have to be committed. Naturally, you can see the data type then consumes resources. When you're done with it, you should free it. The data types effectively have reference count semantics, so as long as somebody is using a data type, the resources don't get freed. You can now duplicate a data type, and there are even attributes on it. This can be important if you're building libraries that take in non-trivial data types as options, because that means that you can make a copy of it that you can then use for your own purposes. There are routines to pack and unpack data, so you can use those instead of doing it yourself. Again, typically that's not useful. There are sometimes when it can be. There are routines that you can be given a data type and then you can unpack it. This is useful for tools. It can be useful for a library if you want to describe a data type that someone else has constructed, or you want to check that what they've given you makes sense. You can take that data type handle and unpack it. In many ways, this is my favorite constructor because it allows you to do some very sophisticated things. It changes the effective, what we call the extent of a data type. When you use contiguous, you put together successive versions of the data type where you use the extent to figure out where the next one goes. So what I can do to create a variable count vector type is resize for example, a double with the length of the stride. And then if I do 7 of those, I will get 7 copies with the stride. And if I do 6, I will do 6 copies with the stride. So if you have, for example, a triangular matrix, this gives you a way to create one data type that can be used for any number of entries. Okay, so as you're trying, if you want to try out the data types, it's like to keep them as simple as possible. Contig is good. Simple, in fact, you don't have to, at the bottom level, you don't have to create them. Vector, there may be some optimizations. Index block takes advantage of the fact that each element is the same length, so requires less data to store. Index is then next, and struct is the worst. It has to store the most data. What's the difference between index and struct? Index has a single base type, where struct, part of the struct is an array of base types. And so this is the generalization from here to here is that array of types. The performance, will this be good for you today? Who knows? Depends on your system. Will it be good for you next year? More likely, but still it will depend on your system.